Okay, so please copy the 4.16 and 4.17 also. These equations will be needed. Just so have you completed? Have you completed copying these two equations?
Yes,
There is
sir.
also Here is also a power cut. Oh. Okay, so what's your name? You are only responding, others are not responding. Okay, so then we are then give heading monthly average and daily global radiation. So because here is a power cut in college, that's why I have joined with my mobile network. So maybe कुछ voice में problem आएगा तो मुझे बताना. I don't know. Here is a power cut from 5 to 10 minutes. 5 minutes हो गया. Okay. So empirical equations for estimating terrestrial solar radiation on horizontal surface और उसमें हम पढ़ेंगे monthly average and daily global radiation. So please एक ये equation पे ध्यान दो 4.18 Hg bar divided by H0 bar is A plus B TD bar by TD max bar. Okay, where Hg bar is the monthly average of the daily global radiation on a horizontal surface. Please see the notation, monthly average of the daily global radiation. Okay, monthly average of the daily global radiation. Again I am saying daily global radiation, but H0 is the monthly average of the daily extraterrestrial radiation. This is your global radiation, but H0 bar is the extraterrestrial. Okay, it doesn't consider the terrestrial radiation. It is the extraterrestrial radiation. Okay, so then your TD bar is the monthly average of the sunshine hour per day at any location. So okay, sunshine hour per day. This will be given in the questions. No need to worry. We have to only calculate the TD max. ओके, टीडी मैक्स का कैलकुलेशन मैंने फॉर्मूला पहले से दिया हूँ आपको, अगर याद होगा 2/15 वाला फॉर्मूला 2/15 ओमेगा एस इज कोसाइन इनवर्स माइनस tan phi tan डेल्टा. ये फॉर्मूला हम पहले किए थे. ये प्रॉब्लम दिस वन टीडी मैक्स यू हैव टू कैलकुलेट. हियर लिखा है ना 2/15 कोसाइन इनवर्स माइनस tan phi into tan delta. Okay, minus tan phi tan delta. Okay, accordingly you have to calculate TD max. So TD max you have to calculate from that formula and TD will be given to you. And please write down these formulas of A and B. These are all empirical formulas. So in this class also, in next class also will be used बहुत सारे empirical formulas use करना है. And these empirical formulas will be given to you during your semesters. So no need to worry. इसको आपको याद नहीं रखना है. इसमें बहुत सारे इक्वेशन आपको दिया जाएगा. जो इक्वेशन आपको नहीं दिया जाएगा वो मैं बता दूंगा. Okay, so please write down this equation 4.18 and 4.19. See, एक ही चीज देखो यहाँ पे, ये जो थीटा लिखा है, that theta is your elevation, sorry, inclination angle, जो हम बहुत बड़ा सा एंगल कैलकुलेट किए थे, that sorry cos phi है, ये थीटा नहीं है, ये phi है. Phi is your latitude angle. Okay, phi is your latitude angle and EL is the elevation. EL is the elevation from the sea level. Okay, EL is the elevation from the sea level. And TD max you have to calculate. Okay, so please write down 4.18, 19 and 20 equation, and please write down all these notation, Hg bar, H0 bar, TD bar, TD max bar. Please write down all the notation. And those who are new also in today's class, I want to tell you कि I have already formed a group and already provided the notes there. Some of the parameters are also missing in the notes. So मैं जो यहाँ पे बोल रहा हूँ उसको एक बार डिटेक्ट कर लो. Okay. So please write down from this 4.18 equation to 4.20 equation. आप लोग का प्रोजेक्ट प्रेजेंटेशन नहीं हो रहा है इंटर्नशिप स्टूडेंट्स के लिए? Can anybody reply?
Yes, sir, it is happening.
Okay. What's your name? आपको छोड़ के बाकी कोई रेस्पॉन्ड नहीं कर रहे हैं. What's your name?
Ashna.
Okay. It's your first class perhaps, na?
No, sir, last Sunday I was there. I had submitted the assignment.
Okay. So, खत्म हो गया इक्वेशन 4.20 तक. अभी हम प्रॉब्लम करने जाते हैं. ठीक है?
Yes, sir.
ओके. सो देखो, मैं आज एग्जाम्पल 4.4, 4.5, 4.6, 7, 8 5 एग्जाम्पल करना है. ये 5 एग्जाम्पल बहुत, मतलब ये तो 4.4 का ही एग्जाम्पल बहुत टाइम लगेगा. सो एक चीज बताना चाहता हूँ, यहाँ जो EL है, दैट EL इज योर एलिवेशन ऑफ द लोकेशन अबव द मीन सी लेवल इन किलोमीटर. ओके, जो भी दिया होगा आप उसको किलोमीटर में एपीटी यूज करें. होता नहीं मैंने लैपटॉप रे यूज होचन. हाँ ठीक है, फुल स्क्रीन कर दो. ठीक है, आ सिमुलेशन देखियो कहले देखिए देबो. ठीक अछि. हां ओके. हां सो विल डू 4.4 प्रॉब्लम. हाँ, मैं ये बोल रहा था कि 4.4, 4.5, 6, 7, 8 ये 4 प्रॉब्लम मुझे 2 कल भी टाइम ले लेगा. सो हाँ, तो हम जाते हैं. देखो, फॉर 4.4 फॉर कोयम्बटूर को दिया है 11.0183 डिग्री नॉर्थ लैटिट्यूड एंड 76.9725 ईस्टर्न लैटिट्यूड एंड एलिवेशन ऑफ 411 मीटर अबव सी लेवल. सो फर्स्ट ऑफ ऑल कन्वर्ट दिस इनटू योर elevation in kilometer, 0.411 kilometer. Okay, so please convert EL equal to 0.411 kilometer and estimate the value of average daily global radiation. Question में पूछा estimate the average daily global radiation, means in question it is asking to find out Hg bar. Okay, in find out Hg bar, average daily global radiation on horizontal surface during the month of the March. See here, there is no day of the March is mentioned, so you have to take mid of the March as your day. Okay, you can take your 15th or 16th of the March is the day. So where you have to calculate the daily average global radiations. Okay, so 15th March, from January 1 to 15th March, calculate the number of days. It will be around 75 days. So please take n equal to 75. Then the average sunshine hour per day for the month of the March may be assumed as 9.5 hour. So what I have assumed 9.5 hour. So TD bar is 9.5. So you have to see कि TD bar is 9.5 hour. So you have to calculate TD max. You have to calculate A, B. Okay. Then you will calculate Hg by H0 bar. Again, you have to calculate H0 bar. You have to calculate A, B, TD max bar. See, the book's answers are not correct. ठीक है, तो इसीलिए मैं बोल रहा हूँ आपको, मैं जब बोल रहा हूँ कि आंसर बताओ, आप डायरेक्टली बुक का आंसर मत बता देना या बुक का आसपास आंसर मत बता देना। चारों क्वेश्चन का थोड़ा आंसर गलत है एंड आपको मैं मतलब मेरे को पता है कि मैंने ये आंसर निकाला हूँ तो मेरे को पता है कौन सा रेंज में आएगा। ठीक है, इसलिए डायरेक्टली बुक का आंसर मत बता देना। आपको बता देता हूँ इसमें क्या करना है। देखो, मैंने क्या बोला था कि आपको जो भी लोकेशन का दिया है, आप अगर लैटिट्यूड एंगल फाइंड करना चाहते हो तो ये आप नॉर्दर्न लैटिट्यूड का डेटा लेना। तो ये ऑलरेडी डिग्री में है, तो योर फाई इज योर 11.0183। जो बुक में थीटा लिखा है दैट इज योर फाई latitude angle and your EL is 0.411, so TD bar is 9.5 hour. So again मैंने क्या बोला था, n आपको फाइंड करना है। n इक्वल टू जनवरी का 31, फरवरी का 28, 59 एंड 15, टोटल इज 74 डेज। ओके, या 75 डेज, अगर आप 16 मार्च तक ले लोगे तो 74 या 75 डेज n। तो इसमें से आपको क्या निकालना पड़ेगा, पहले देखो, पहले चीज आपको टीडी मैक्स निकालना पड़ेगा। ठीक है, तो टीडी मैक्स का क्या फॉर्मूला है मैं दिखा देता हूँ। टीडी मैक्स का क्या फॉर्मूला है, टीडी मैक्स इज 2/15 कोसाइन इनवर्स माइनस tan फाई इंटू tan डेल्टा। ओके, और एक बार बोल रहा हूँ, 2/15 ये जो फॉर्मूला लिखा है, कोसाइन इनवर्स माइनस tan फाई इंटू tan डेल्टा। ओके, माइनस tan फाई इंटू tan डेल्टा। सो वी हैव टू कैलकुलेट टाइम, वी हैव टू कैलकुलेट फाई फर्स्ट। फाई हमारा हो गया, फाई हमारा कितना डिग्री है, 11.0183। सो यू हैव टू कैलकुलेट डेल्टा। सो व्हाट इज द फॉर्मूला ऑफ डेल्टा? आई हैव ऑलरेडी टोल्ड यू, 23.45 sin 360/365 into 284 plus n। ठीक है, प्लीज कैलकुलेट डेल्टा फर्स्ट। Please calculate delta first. After calculating delta, you have to use and calculate omega s. So when we'll calculate omega s, we'll multiply 2/15. You will get the TD max value. Then I will proceed. Okay. Please take your time and calculate delta first, then TD max. Okay. Can you proceed? अंशा, जो व्हाट्स योर नेम मैं भूल गया। Can you proceed? समझ में आया क्या करना है?
Yes, sir. Sir,
Okay, please. हाँ,
can you show the formula of TD once again?
TD 2/15 cosine inverse minus tan phi into tan delta। ओके, यहाँ पे लिखा है, देखो ये phi का वैल्यू है आपका 11.0183। ठीक है, आपको phi का वैल्यू है 11.0183। एग्जैक्टली ये मतलब डेल्टा का एग्जैक्टली इतना नहीं आएगा, इसीलिए बोल रहा हूँ आपको कैलकुलेट करने का। tan डेल्टा, डेल्टा इज, इसका डेल्टा आ रहा है -2.4177, सो माइनस tan phi इंटू tan डेल्टा। ओके, एंड एक चीज और करना, देखो ये जो ब्रैकेट में कोसाइन इनवर्स इसका वैल्यू है, ये है आपका ओमेगा एस, सनशाइन आवर। इसमें मैं अगर 2/15 मल्टीप्लाई करूंगा तो मेरे को सनशाइन इन आवर में देगा। तो ये जो एंगल आया 90.47, ये नहीं आएगा, ये इससे कम आएगा। मतलब ये कितना डिग्री आएगा आप कैलकुलेट करना, और उसको आप रेडियन में कन्वर्ट भी करना, पास में लिखना। ठीक है, जो डिग्री लिखे उसको आप रेडियन में भी कन्वर्ट करना। कैसे करोगे, 1 डिग्री 180 डिग्री इज पाई रेडियन, 1 डिग्री इज पाई बाई 180। ठीक है, प्लीज ट्राई फर्स्ट कैलकुलेट डेल्टा, देन ओमेगा एस, देन टीडी मैक्स वैल्यू, देन विल प्रोसीड। ये एक प्रॉब्लम ही ले लेगा 15-20, मतलब आधा घंटा ले लेगा। सो प्लीज प्रोसीड। How much you got delta? Have you calculated delta value?
Sir, it is coming the same minus 2.417.
Okay, and how much omega is?
Sir, doing.
Okay. Except Ansha, anybody doing? Supriti, are you there?
Yes, sir, doing it. I've got the delta same, and then I've calculated the TD max. Now I am doing that omega s.
Omega s is 2 by 15 into, sorry, TD max is omega 2 by 15 into omega s. First you have to calculate omega s, then TD max value. Okay? First calculate omega
Okay,
s value. And how you people's internship going on? Good?
Yes, sir.
Okay. Internship is work from home, yeah, you have to, means physically you are present in the company.
Physical.
Physically, sir.
Okay. So it is quite tough. At a time you have to manage your semester in Saturday, Sunday, and your project and internship. But be specific. Be specific towards your internship first. You have to be serious about your semester also, but be specific to your internship. एट फोर थ्री फोर सिकेश व्हाट्स योर नेम चंदन कुमार क्या नाम है हैव यू मतलब आर यू फॉलोइंग मी क्या कर रहे हो अभी क्या कैलकुलेट कर रहे हो
Actually, I got a call from my office, so I haven't from last 5 minutes.
Okay. Angana.gm, what's your name? Okay, just apart from studies, I am asking, it is very difficult to manage both internship and semester at a time. Please share your experience. It is very difficult at a time because Saturday, Sunday you have to take your class from 10 to 6.
Yes, sir.
Okay, that's why I am asking. Which company you are in?
Ericsson.
Ericsson, okay. And Supriti, you are in which company?
Tejas Networks.
Okay. और कोई है कोई डेलोइट में है यहाँ पे स्टूडेंट्स ओके व्हाटएवर इट मे बी प्लीज बी सीरियस टू अबाउट योर इंटर्नशिप ओके एट ए टाइम मैनेज करना भी बहुत डिफिकल्ट है बिकॉज सैटरडे संडे भी एंड एज यू आर इंटर्न सो आपके ऊपर तो बहुत काम आ रहा होगा मतलब बहुत कुछ उधर भी नया सीखने को मिल रहा होगा नया सीखना भी चाहिए एंड करियर भी है ऊपर से इधर भी आपको मतलब सेमेस्टर भी कंप्लीट करना है इट्स लिटिल बिट टफ एंड एज यू पीपल आर मतलब जूनियर इन योर एज यू पीपल आर इंटर्न ऑल्सो नाउ सो आपके ऊपर तो बहुत प्रेशर आ रहा होगा यस और नो अरे प्लीज शेयर नो नीड टू वरी यस और नो एम आई राइट
Yes, sir.
Yes, sir.
Chinmay Kumar Sahu, are you there?
Yes, sir.
Which company are you in?
Tata Elixir.
Okay, Tata Elixir. Your posting is in which city?
Pune.
Okay, it's a great place. Have you ever visited Lonavala?
No, sir, we're planning to visit. Lonavala is like 150 to 200 kilometers from here.
Okay, okay. Do visit there and also थोड़ा मैं बोल रहा हूँ अभी बहुत ज्यादा पता नहीं पुणे बेंगलोर में क्लाइमेट कैसा है, गर्मी तो आ गया होगा, प्लीज
हाँ सर,
मतलब हाँ थोड़ा अपना सेल्फ केयर करो पहले, वो बहुत नेसेसरी है। योर प्रायोरिटी शुड बी सेल्फ केयर, देन इंटर्नशिप, देन योर सेमिस्टर।
yes sir.
Okay, please calculate omega s and TD max.
Sir, TD max is 11.975 hour.
Okay, and omega s is how much degree?
89.81 degree.
89.81. Please convert it into radian.
1.568 radian.
6. Okay, yes, correct. देन एक बार आपका ओमेगा TD मैक्स हो गया, देन आपको क्या करना है, जस्ट 1 मिनट, देन यू हैव टू यूज जो H0 का आप फॉर्मूला लिखे थे, गॉट माय पॉइंट, जो H0 का आप बहुत ये वाला फॉर्मूला लिखे थे 3600 into 24 pi, दिस फॉर्मूला 4.15, गॉट इट, you have to use this formula, okay, and you have to use solar constant ISC as 1.36. At my point, ISC as 1.36, it is a fixed constant value, and n is your 75, and cos theta नहीं, ये cos phi है, phi is 11.0183 degree, delta you have, omega s sin, जहाँ पे आपको sin omega s दिखा, आप please use the omega s in radian, sin omega s, cosine omega s, आप please use the radian, degree value, and जो खाली omega s है, उसमें आप radian value यूज करो, ठीक है। डेल्टा है आपके पास, थीटा मतलब फाई है आपके पास है, सो प्लीज कैलकुलेट H0 यूजिंग दिस फॉर्मूला, प्लीज कैलकुलेट H0 एंड द यूनिट विल बी किलो जूल पर मीटर स्क्वायर, गॉट इट अंसा? एंड सुप्रीत यू गॉट इट? प्लीज कैलकुलेट करो एक बार, ठीक है, टाइम नोट, हाँ टाइम नोट कैलकुलेट करो, बिकॉज एक बार प्रैक्टिस हो जाए तो हो जाएगा, एंड ये फॉर्मूला आपको एग्जाम में दिया जाएगा, नो नीड टू वरी, इसमें से बहुत सारे फॉर्मूला दिया जाएगा आपका सेमेस्टर के पहले, मैं बता दूंगा कौन सा फॉर्मूला आपको याद रखना है। एंड जो प्रीवियस 2 क्लासेस में जो मैं न्यूमेरिकल सॉल्व किया था, आज ये क्लास खत्म होने के बाद मैं उसका सोल्यूशन अपलोड कर दूंगा।
Yes.
SI टाइप का क्वेश्चन आएगा मिड सेमेस्टर या एंड सेमेस्टर में, सो मैं उसका सॉल्यूशन अपलोड कर दूंगा।
सर प्रीवियस क्वेश्चंस में जितना भी आर एंगल कैलकुलेट किया है, आर एंगल इट इज नॉट सेम इन द बुक, मतलब बुक का कुछ मिस्टेक है दैट मींस।
कोई दिक्कत नहीं, एक्चुअली वो सोलर टाइम एंड स्टैंडर्ड टाइम को मैंने सेम ले लिया हूँ, ठीक है, तो वो स्टैंडर्ड टाइम एंड सोलर टाइम को अलग ले रहा है, उसके लिए वो कुछ एरर कैलकुलेशन कर रहे हैं, तो इतना डिटेल में जाना जरूरत नहीं, मैं डायरेक्टली सोलर टाइम और स्टैंडर्ड टाइम को सेम ले लिया हूँ, गॉट माय पॉइंट, दैट्स व्हाई वी आर गेटिंग डिफरेंट आंसर, ठीक है। एंड एक और चीज, आपको अगर एग्जाम ऑनलाइन होगा, मतलब आपका तो ऑनलाइन होगा, मतलब कैसा एग्जाम होगा उसके बेसिस पे नो नीड टू वरी, मैं मिड सेमेस्टर के पहले आपको 20-25 क्वेश्चंस, 30-35 जो टाइप ऑफ क्वेश्चंस दे दूंगा, नॉट एग्जैक्ट क्वेश्चन, आपको टाइप ऑफ क्वेश्चंस दे दूंगा, उसमें से आएगा, ठीक है। एंड आपको मतलब जैसे कि सेमेस्टर आएगा मैं बता दूंगा कौन सा फॉर्मूला, एक फॉर्मूला सीट भी दे दूंगा, गॉट माय पॉइंट, एक फॉर्मूला सीट दे दूंगा ताकि आपको इजी होगा, उसमें से कौन सा फॉर्मूला याद रखना है वो भी बता दूंगा, ठीक है। सो प्लीज कैलकुलेट H0। हाँ, एग्जाम क्या बोल रहे हो?
एग्जाम ऑनलाइन होगा या ऑफलाइन?
ये मेरे को आइडिया नहीं है, ऑब्वियसली आपका 7 सेमेस्टर जैसा था ऐसा ही होगा मुझे लग रहा है। अभी तो आपका नॉर्मल स्टूडेंट का भी ऑनलाइन क्लास हो गया है, आपको पता होगा, नॉर्मल स्टूडेंट का भी ऑनलाइन क्लास हो गया है, तो देखो इसीलिए बोल रहा हूँ, जैसे होगा उसके हिसाब से, अगर मल्टीपल चॉइस MCQ वाला हुआ तो मैंने उसके हिसाब से आपको 100-150 MCQs दे दूंगा प्रैक्टिस के लिए, और अगर ऑफलाइन मतलब अगर जैसे कि होता है ऐसा अगर हुआ, मैं 30-35 क्वेश्चन दे दूंगा प्रैक्टिस के लिए, उसी से ही आएगा, थोड़ा डेटा इधर उधर होगा लेकिन उसी से ही, मतलब फ्रेम ऑफ क्वेश्चन विल बी सेम। एंड मैंने आपको एक नोट्स दिया था, अगर आप कोई ग्रुप में नहीं हो तो मुझे एक बार मैं नंबर बोल दूंगा, एक बार आप लोग का दोस्त के पास भी होगा, आप ले लो एक बार वो नोट्स, आप पढ़ सकते हो, 80 पेजेस का है, ठीक है। ओके, प्लीज एक बार H0 कैलकुलेट कर लो। ये थोड़ा टाइम लगेगा, H0 कैलकुलेशन थोड़ा डिफिकल्ट है, लेकिन अपना टाइम लो और H0 कैलकुलेट करो। इसके बाद हमें A और B का वैल्यू कैलकुलेट करना है। जस्ट 1 मिनट, आई गॉट अ मैसेज फ्रॉम माय HOD। जस्ट मैं एक बार चेक करके आता हूँ, जस्ट 1 मिनट। सो एक बार H0 का वैल्यू कैलकुलेट कर लोगे तो मुझे बताना, एंड द यूनिट विल बी किलो जूल पर मीटर स्क्वायर है। Have you completed? Have you completed H0? What is your value?
Yes, sir.
What is the value?
37,203.99.
Okay. Then after you get H0, so see, in these questions he is asking Hg bar. So you have TD max value and you have TD value given in the question is 9.5. So what is our task? Our task is to calculate A and B. So use this empirical formula and calculate A and B. So your TD bar is 9.5. It's given in the average sunshine hour in Coimbatore location is given 9.5, and you got your TD max is something 11 hour something, 11 point something you have got. So EL is 411 meter. Coimbatore is 411 meter above the sea level. So above the sea level means you have to convert it into kilometer, 0.41 kilometer, and your phi, theta, phi is your given in the questions 11.0183. It's 11.0183. So you can use the formula and calculate A and B. Okay, please calculate A and B. Those who have completed, please calculate A and B.
Sir,
हाँ
I have
हाँ
doubt in H0. Can you explain it again?
हाँ. See, you have theta with you. Theta means phi. You have phi with you. Yes or no?
Yes, sir.
You have delta with you. Calculated minus 2.417.
Yes, sir.
And you have omega s with you. 89 point something.
Yes, sir.
And please convert it into radian.
Okay. And ISC.
ISC is the solar constant. I have told you, na. ISC is the solar constant. Its value is 1.367. Okay. You can directly take it 1.36. इसके बाद हो जाएगा ना?
हाँ, yes, sir.
Okay. Please do A0.
And N is 75.
N is 75. एक और चीज देख लो. इसके बाद हमें चाहिए ये फॉर्मूला में TD by TD max. TD bar is 9.5 and TD max bar you have calculated around 11 point something. चेक कर लेना. And हमें चाहिए क्या? A and B. तो you have to use this formula. Theta is your phi जो 11.0183 डिग्री आया है and EL is your 0.411 because Coimbatore location is situated 411 मीटर above sea level. So आपको EL डालना है 0.411 किलोमीटर. ठीक है? Then use the formula, calculate A and B. Okay?
Okay, sir.
हाँ. So please calculate H0 and A and B. आपको H0 फॉर्मूला ये है. आप एक बार स्क्रीनशॉट भी ले सकते हो H0 फॉर्मूला का. 3624 by pi cos theta cos delta sin omega s. ये वाला फॉर्मूला यूज करना है H0 का. देन A and B फॉर्मूला. सो हमें कैलकुलेट करना है Hg बार. ही इज आस्किंग मंथली एवरेज डेली ग्लोबल रेडिएशन ऑन हॉरिजॉन्टल सरफेस एट लोकेशन कोयम्बटूर. ಸರಿಯಲ್ಲ? ಒಟ್ಟು ಮಿನಿಟ್. So have you calculated H0? Have you got the answer H0, A and B?
Yes, sir.
What is H0?
Sir, A and B calculated.
Okay, H0 you have calculated. Well, can you please tell me H0 value first?
Yes, sir. 1 minute, sir. H0 was 11 point.
H0,
11 point.
H0, not 11. TD max is 11 point something
Oh,
hour.
sorry,
H0 I
sorry.
am asking.
Oh, no, sir. Calculating. H0 was 37,399. 0.399.
Yeah. Yeah. Then you have A, you have calculated. What is A value?
A is 0.4216.
And B is
0.294.
0.294. Okay, let me check. B is 0.294. Okay. Then you have to use this formula. Hg by h naught is a plus b td bar by td max bar. Td bar is your 9.5. In question it is given ki the sunshine in assumed is 9.5 hour. So 9.5 hour divided by td max, you have calculated 11 point something. You have a value, b value. Please cross multiply H0. You will get Hg bar value, means monthly average of the daily global radiation. Okay, that is he is asking. Monthly average of the daily global average radiation. Have you calculated? Have you calculated HG bar?
Yes, I am getting 23,345.28.
Okay, please write that as kilojoule per meter square. Kilojoule per meter square. Okay, so that is your monthly average global radiation, monthly daily. So in question it is asking to find out the estimate the value of average daily, not monthly, sorry, daily global average radiations. Okay, so please write down that one, daily average global radiation. ये और कोई कुछ बोल रहे हैं टी. ओके, देन हम चलते हैं और एक और एस्टिमेट की तरफ. सो प्लीज राइट डाउन मंथली एवरेज डेली डिफ्यूज रेडिएशन. So what is diffuse radiation? I have told you कि diffused plus beam radiation is equal to global radiation. So जो हम previously अभी पढ़ के आए that is your global radiation. अभी हमें diffuse radiation पढ़ना है, मतलब कितना diffuse हो जाता है, कितना absorb हो जाता है atmosphere में, ठीक है, radiation कितना absorb हो जाता है, that is your diffuse radiations. Okay, monthly average diffuse radiations. So to get that monthly average कितना power cut होता है? So to get the monthly average daily diffuse radiation, we are using generally two empirical formulas. That is your Gopinathan and Solar formulas, and another is Garg and Garg formulas. Okay, please give heading monthly average daily diffuse radiations. Please give heading monthly average daily diffuse radiation, and give subheading Gopinath and Solar. Okay, Gopinath and Solar formulas. ठीक है, please give heading monthly average daily diffuse radiation, and see we'll use these formulas 4.21 and 4.21 4.21 and your 4.22 for Garg and Garg. First one is Gopinathan and Solar. Okay, 0.87813, these are all empirical values. Minus 0.3328 kT bar, माइनस 0.353039. ये वैल्यूज अब आप 2 डिजिट तक लिख सकते हो, इतना ज्यादा करना जरूरत नहीं है, जस्ट 2 डिजिट TD बार बाय TD मैक्स बार, ठीक है. एंड व्हाट इज योर KT इज योर Hg बाय H0 नॉट, जो हम प्रीवियसली पढ़ के आए, जो A प्लस बी TD बाय TD मैक्स था, वो ये जो वैल्यू है ये है आपका KT. एंड दिस इज कॉल्ड योर मंथली एवरेज क्लियरनेस इंडेक्स भी बोला जाता है इसको, ठीक है. तो आपको मैं भी डायरेक्टली पूछा जा सकता है कि अकॉर्डिंग टू गोपीनाथन एंड सोलर फॉर्मूला व्हाट इज योर मंथली एवरेज क्लियरनेस इंडेक्स. सो अब क्या करना, Hg बार बाय H0 बार को डिवाइड कर देना, ये हो गया आपका मंथली एवरेज क्लियरनेस इंडेक्स, ठीक है. तो आप प्लीज ये प्रीवियस फॉर्मूला लिख लो, ये जो 4.21 का इसको बोला जाता है गोपीनाथन एंड सोलर, एंड ये आपका है जो नीचे वाला 4.22 का है, ये है गर्ग एंड गर्ग, ठीक है. एंड ये KT का भी लिखना, ये 3 फॉर्मूला लिखना. इसके बाद मतलब हम इसका प्रॉब्लम नेक्स्ट क्लास करेंगे, इसका प्लीज ये 3 फॉर्मूला लिख लो जस्ट. Have you copied? Have you copied the three equation?
Yes, sir.
ओके सो ये इसका हम प्रॉब्लम कल सॉल्व करते हैं और मैं आज ही ये खत्म होने के बाद आपका जो प्रीवियस क्लास का न्यूमेरिकल है वो मैं अपलोड कर रहा हूँ वो मैं जस्ट अपलोड कर दूंगा जस्ट 1 मिनट यहाँ पे कौन कौन है चंदन कुमार सामल हु इज angana.gm please respond anybody knows his name angana.gm please उसका नाम बता दो
Yes, Angana Ghosh Majumdar, sir, section E.
ओके ओके ठीक है
Yes, sir, Angana.
आशुतोष ओके अंगना घोष मजुमदार ठीक है आशुतोष रथा अतीश कुमार 372 व्हाट्स योर नेम व्हाट्स योर नेम
सुश्री श्रेया मिश्रा.
ओके शुभम पटनायक श्वेता पद्मा दास ओ तेजस पाढ़ी 2844884 व्हाट्स योर नेम
अनन्या मोहंती.
अनन्या मोहंती ओके ठीक है just let me take a screenshot then you people can leave okay एक्चुअली अटेंडेंस शीट मीट में भी जो डाउनलोड होता है आपका यही नेम से डाउनलोड होता है इसीलिए मैं लिख के रख रहा हूँ ठीक है ओके यू पीपल कैन लीव नाउ हम कल वो प्रॉब्लम सॉल्व करेंगे यू पीपल कैन लीव नाउ
Hello, okay, there was some network issue. So let's continue again. Okay, so I hope my screen is visible. So you can hear that this ABD, these are input signals, so you can separate them by using commas. So after that colon, then you
Sir,
have
screen is not visible.
Okay, I'll say it again. Whether it is visible now? Hello?
No, sir.
It's not visible? Okay, just. So is it visible now?
Yes, sir.
Okay, thank you. So here you can see that the ABD, these are the three input signals. So you can separate them by using comma. Then you have to give column. So next you have to specify the mode. Okay, so you have to specify the mode. So here mode is what? In, as these are input signals. So mode is in. So then you have to specify the data type. So here the data type is bit or binary digits. So 0 and 1. These are your we are taking as the inputs. So after that you have to give semicolon. Then next you can see the E. This is the output signal. So next you have to write this name, that is E colon. Then you have to specify the mode. Here mode is out, and next you have to specify the data type. Here that is bit. So after that you have to write what? End. Then you have to specify this entity name. So entity name here you have given as 2 bits. So this is how we can do the entity description. Okay. So entity space entity name is here port declaration. After that end keyword. Then after that you can write this entity name. Similarly, you have to do the architecture description. So here you see how we can do the architecture description. That is, you have to use the architecture keyword. Then here you have to write what? Architecture name. So here architecture name we are giving as gates. So whatever name you want, you can give. Then of. Then here you have to specify the entity name. So here the entity name will be same as what we have already mentioned here. So this name you cannot change. Means if here you have mentioned 2 gates, means here you have to write that name. Then is. So here then the signal declaration, you can see here that this C, this is the internal signal, that is the, we can say that this is out for this AND gate, and this is in for this OR gate, which is an internal signal. So you can, then the name is C, and you can mention here the type is what? That is bit. So here this is not in or out, this is considered as the internal signal. So here you can mention what is its type, data type, that is bit. Then after that you have to write the body within this begin and end. So what we are going to do here, what operation we are going to do here, we are doing the AND operation. Next is the OR operation. So here C, then this symbol, you know, this is the signal assignment operator. So C equal to A and B. So as you know, here A and B, these are the input. So C equal to A and B, and this E, this will obtain what, which is nothing but E equal to C or D. Okay. So these are the concurrent statements. As you know, these are what this double dash symbol, these are used for comment lines. So these are the concurrent statements that we are going to execute. So whenever any changes in this A, B or D, whatever, if it changes, so these statements will be executed again. So then after that end, then you have to specify what, that is the architecture name. So this is the you can see the VSDL code for this circuit. So this entity description you can think of as a black box where you can see only the input and output. Here, what are the input? You can see that A, P, D, these are the inputs you're taking, and E, this is the output. So, like here we just saw that we can describe a system in VSDL. For describing a system in VSDL, we must specify the entity and architecture at the top level, and then also we need to specify the entity and architecture for each of the component. Like here, next here we'll see like the example of a 4-bit full adder. So where you can see that consists of what 4 full adders. So where each of the full adder we can say that these are the components. So there are 4 components of this 4-bit full adder you can see. So first we need to describe the system in VSDL. First we will describe at the top level, like you can see for a 4-bit adder we will describe at the top level. Then we'll specify an entity and architecture for each of the component modules. Like this will be done at bit level. So for like each bit will take one adder. So that's what we'll specify at the component level also. So your entity declaration, as we discussed, this includes a list of interface signals. So you can see this declaration form that we discussed entity. Okay, then entity name we have to give is, then within square bracket we have mentioned port interface signal declaration. As you know, whatever we are mentioning within the square bracket, those are optional. So hello, okay. So either means this can be written or this can be omitted. So these are optional. So similarly, and entity, this entity you can write and then entity name. So all these are optional that we have written within square brackets. So here we have just mentioned the entity name. You can see that entity name we have written, that entity name is gets. Okay. So as we discussed, entity, the items which are enclosed in the square bracket, they are the optional. So then this interface signal declaration, this just 1 minute, Sivendra sir is calling. Okay, so now just see that as I told that items which are enclosed in the square bracket, as you know, these are optional. You may or may not specify those. So the interface signal declaration, you can see this is the syntax. So here list of interface signals, then column, then you have to specify the mode, that is in, out, or this may be in, out, or this may be buffer. These are the various modes. So you have to specify. Then type, the data type you need to specify. Then if we want to initialize it, so that is optional. If you want to initialize it, so you can specify this colon equal, this stands for the assignment. So you can give some initial value if you want to initialize. So like this, this can be repeated. Here you can see that this whatever we have written within this curly brackets. So this indicates what? 0 or more repetition of this. Okay. So the same thing I mentioned. So 0 or more repetition of this. After that, as you know, each statement ends with semicolon. So you have to give semicolon. Okay. As I told that here mode, this can be what, like in, out, or in, out. Okay. So there are various modes, or this may be buffer mode or linkage mode. These are the modes, various modes we'll see. So in the previous example, what we saw that we have used these modes in and out. So that we have seen that ABD, these are the input signals, and this E is the output signals. Okay, so as I told that this initial value, so this is optional. If you want to initialize, then you can initialize it with giving some initial value. So here you can see, for example, here another example you can see, let's say, okay, here port AB we are taking, all these are what we are taking input signals. So that's why you have mentioned here what, in. Then you need to specify the type. Earlier we have mentioned that those are bit. Now let's say we are taking it as integer. So integer means now you can assign that with any integer value. So like here we are initializing it with the value 2. And next you can see that like CD we are taking, these are the output signals. Okay. And so that's why here we have mentioned this out, and we are declaring the type is bit. So this is an example of a port declaration where you can see that this AB, these are the input signals. So where we have initialized it with the value 2, and these C and D, these are the output signals, and they are of type bit. Okay, if will not initialize these, so by default they will be initialized to 0. Like here we have initialized them with the value 2. If will not initialize those, so they will be by default initialized to 0. So like we told that these modes in, out, and in, out. Apart from that, there are two other modes also, as I told, that buffer and linkage mode. Okay. So two other modes are there, like buffer and linkage mode. So as the name suggests, here you can see that in is used for like input signals and out for output signals. In, out means it can both be used as input and output signals. Similar to that, two other modes are there, like buffer and linkage. So your buffer mode is similar to your in-out mode. Okay. Means it can be read and written into an entity. So that's what this is. Buffer mode is similar to your in-out, which can be used for reading as well as writing. But this buffer, this will be useful when that if signal is truly an output, but we like to read the ports internally as well. So we'll see the example of that buffer mode. In the next example, we'll see. So this just previously what we discussed, VHDL program structure, like first entity structure, entity architecture. Then you can see that there may be various components, as I discussed, a 4-bit full adder we are discussing, like 4-bit full adder that will be having the 4 components. That is, will take, but that is 4 full-bit adders. You can see that here 4 full adders we are taking. Means if you are taking what, 4-bit binary adder, okay, 4-bit binary adder, then you have to take what, 4 full adders. So where each of these are components of that 4-bit binary adder. So here, okay. So as I told that, so this buffer mode, we'll see the example, and the linkage port, this will be useful when the VHDL entities are connected to non-VHDL entities. If you are connecting VHDL entities to non-VHDL entities, at that time this linkage port will be used. Now you see the example here. Okay, now this structure, just to see that I told that entity architecture, then all these are components like module 1, module 2 up to module n, n components are there. So this is a declaration like architecture name of entity name. So this as we discussed in the previous example. So you have to write this architecture is the keyword, then you have to write the architecture name, then of keyword, then entity name, whatever the entity name you would have already specified. So that entity name will write, then is keyword, then whatever the declaration, that declaration will write like in the previous example here, signal C, which is the internal signal that we have declared. Okay. So here whatever the declaration, as you can see this we have written within square bracket. So this is optional. So if any declaration will be there, we'll do the declaration here. Then you have to write this begin keyword. Then you have to write the architecture body within this begin and end keyword. Then you can see that within square bracket in bold we have written architecture means this is optional, and this architecture name also, this is optional. So you may write the architecture name here or you may not write. In the previous example we have written this architecture name, like architecture name we have taken as gates. So here we have written and gates. So actually here it is written in bold, this architecture name, no need to write in bold. If you are writing word simply architecture, this we need to write in bold. Architecture name, no need to be written in bold. Okay, so this is the declaration section. As I told that we can declare the signals, like in the previous example we saw that we have declared the signal C and components that are used within the architecture, so that we can declare here. So your architecture body, this will be consisting of statements which describe the operations of the module. So next, just see here, we'll see the example of a full adder. So first we'll consider a full adder, and later we'll see the 4-bit binary adder. So now you see the full adder. What is the job of a full adder? As you know, here it adds 2 bits and a carry input, and it produces the sum bit and carry output bit. As you know that that is what we are doing in a full adder. So these are the inputs. Okay. So these are the 2 bits or binary digits. Another is carry in, and output is what? We'll find the sum, and C out. This stands for carry out. Okay. So here the entity specifies the inputs and outputs of the adder model, right? Like in the previous example, already I have seen that whenever we are describing the entity, you need to specify the inputs and outputs of the adder model here. So you can see this is the VHDL code, that entity space entity name. So entity name here we have given as full adder. We are using the full adder. So we have given the name full adder. Then each keyword. So after that you have to write this. You have to do this port declaration. So port, what are the input signals over here? You can see that AX, Y, C in. Okay. So you can separate them by using comma. X, Y, C in column. Type is what? All these are input signals. So you have to write in. Then, this is the mode. Okay. Then type. Mode is what? That is the input. These are the input signals. Then the data type. So all these are bits or binary digits. As you know, that will be consisting of what? The value zeros or ones. So here that we are considering what? Only 0 or 1. Okay. So a single bit. And here what is the output? You can see that C out, another is sum. So you can separate them by using comma. And here, as you know, the mode is what? Out. The data type is bit. Then you have to use the end keyword, and then you have to write this entity name. The entity name is your full adder. So this is the entity what we saw. Then the operation of the full adder, how it can be described by using the architecture declaration. So this is the entity declaration. Next is the architecture declaration. So as you know, what is the syntax? That is architecture space architecture name. So here architecture name we have taken as equations. Okay. So architecture space architecture name of, then you have to specify this entity name. What is the entity name? We have taken full adder. So you have to write that name only. So is, then you have to write the begin keyword. And these are the concurrent assignment statements. So what operations we are going to do. As you know, what we do in case of full adder. So we find out the sum and the cout. So how you find out the sum? By doing XOR. So you have to find out XOR of all these input bits. So like X XOR Y. Okay, X XOR Y, then XOR Cin. Okay, and here we have assumed a delay of 10 nanoseconds. So as you know, this in VHDL, so this is also optional. Here we are using a propagation delay of 10 nanoseconds. So that's why here we have written after 10 nanoseconds, after 10 ns. So you know, this is how you find out the sum. Sum equal to X XOR Y XOR Cin. And how we find out the cout? That you know that you have to find what you need to OR all these part, that is X and Y. Okay. Then similarly X and Cin, then Y and Cin, and you have to find out the OR. As here we are using what? And OR. So first you have to find out this AND. Okay, so that's why we need to parenthesize this. So X and Y within parenthesis, X and Cin within parenthesis, and Y and Cin within parenthesis. So after 10 nanoseconds, then you have to write this end and this architecture name. What is the architecture name? We have written equations. As you know, this is also optional. So here you have specified the architecture name. Architecture name is equations. So, like just all of you know this, right? How to do this XOR. In case of XOR, you know that if let's say this is X, Y, what is the truth table of XOR? So X you know, when the bits are different, the output is 1. Okay. When the bits are same, the output is 0. As you know, this is the XOR truth table. So here similarly, you can just see this truth table for the full adder. Okay, so truth table for full adder. So what we are using here, as you know, this sum equal to what? X XOR Y XOR Cn. Here, let's say here A, B, Cn. Now you can think of this AB as XY. So XY Cn. Yes, now just find out this truth table. So what you're taking here, that X Y then Cn, then you know sum, C out, okay. So let us consider, suppose X, Y, and all these are zeros. Then let's take 0, 0, 1. What are the possible combinations? You know, here there are the 3 bits. So total how many possible combinations will be there? You know, 2 to the power 3. So 8 possible combinations will be there. 0, 0, 1, then 0, 1, 0. 0, 1, 1. Okay. 1, 0, 0. 1, 0, 1. So 1, 1, 0. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. 8 possible combinations. Okay. So how to find out this sum? As you know, sum equal to what? So X XOR Y XOR Cn. So this you know that X XOR Y XOR Cn. This is associative. First, like you can find out X XOR Y. Okay. Then you can find out what is the result. Again XOR with Cn. Okay. So that is what we'll get. So X XOR Y when both are 0. Okay. So X XOR Y. So that is 0. Okay. Again that is XOR with Cn, which is 0. So X XOR Y, this is 0. Again XOR 0. As you know, this is equal to 0. So here we'll get the value of sum equal to 0. Like let's say next one, I will find out sum. So X XOR Y XOR Cn. So here 0 XOR 0. So that is 0. Then XOR Cn. So that is 0 XOR 1. So that is nothing but 1. So 0, 1. So like this, you'll find out all this by using this truth table. You can see that, okay, 0, 1, like this, you'll find out this sum. And this C out, as we discussed how to find out the C out. Okay. So C out, you need to find out X and Y. Then or X and Cn. then OR Y and Cin. Like if you'll find this, what will be the C out over here? So here X and Y 0 and 0, as you know, the AND table of 0 and 0, so here we'll get 0. Then or here X and Cn, that is 0 and Cn, that is also 0. Then Y and Cn, that is also 0 and 0, that is 0. So 0 or 0 or 0, so all are 0. So like here we'll get C out as 0. If we'll go for this one, so X and Y, that is 0 and 0. First we'll get what? 0 or. Then X and Cn. So X is 0, Cn is 1. So 0 and 1. As you know, in case of AND, what happens when both of them are 1? The result is 1, otherwise that is 0. So again, here we'll get 0 or. Similarly, Y and Cn. So Y value is 0, then and Cn, 0 and 1, that is 0. 0 or 0 or 0. So like here we'll also get 0. Okay. Like you know the and or table, like in case of and, if both of them are 1, the result will be 1, otherwise it is 0. And in case of or, if both of them are 0, otherwise it is 1. Like that, you can find out this sum and C out. So this is the truth table for the full adder circuit. Okay. So here you can see the architecture name that we have used what? Equations. This is the architecture name that we have used. And the BSDL assignment statements for sum and C out. These are nothing but the logic equations for the full adder. Okay, how to find out the sum and how to find out the C out. These are the logic equations for the full adder. And this is the propagation delay that we have used. So after 10 nanoseconds. So as I told that we need to use the parenthesis. Here we want to perform the AND operation before the OR. So here we need to use the parenthesis, as the BSDL does not specify the order of precedence except for the NOT operator. So we need to use the parenthesis over here. So this what we saw, that is for full adder. So here we are using what? 1 bit. That is bit is either 0 or 1. So this is the that entity description, and this is the architecture description, and this is the truth table for the full adder. Okay, next we'll see this 4-bit full adder. Right? So we'll see how to use this full adder module. So this full adder module, what we just saw now, so this will be used as a component in a system, because we are going to use 4-bit full adder. So where we are going to use 4 full adders, so where each one will be a component. Okay. So how we can do that? Like we need to declare the 4-bit adder as an entity. Okay, so we need to declare the 4-bit adder as an entity. So like in the next figure you can see. So just first see this figure. Okay, first see this figure. So we are going to use what? 4-bit full adder. So here we are using this 4 full adders. Okay. So where each of these adder will add what? 2 bits. Okay. Like in the previous example we saw 1 full adder. So where it will be adding 2 bits along with what? Carry in, C in. So here like first full adder we can see A0, B0. These are the bits, and here C in, that is the carry in is CI, and sum it will produce what? Sum and C out. So here sum for the first full adder, that is S0, and C out is C1. So which will be now used as the carry in for the next full adder. So for the second full adder, you can see that A1, B1, these are the input bits, and we'll find out the sum, that is S1, and this is the carry in, that is C1, and output will be C2. So like that. So here what we need to do is we need to first declare the 4-bit adder as an entity. Okay. And the input and sum output, as you can see, there will be 4 bits wide, because here we are using 4-bit adders. Like we may take one input is, let's say 1 0 0 1, another say, let's say 1 1 0 0. Okay, so all these are 4 bits, and your sum, that will be also 4 bits. Okay, so your A, B, and the sum, whatever we found, sum that will find. So all of them will be 4 bits wide. So for this, what we can do, that we can use the concept of array, as you know, that we can use the bit vector. So now how we can use, the here, or the bit vector declaration here, 4 bits. So it will be from 3 to 0. As you know, the first one, that will be MSB, or most significant bit. We can say, let's say, suppose we are declaring A as a 4-bit vector. So A3, that is the MSB. Here you can say this will be what? Your A3, this one, then A2, then A1, then A0. This is your A3, A1, and A0. Okay, so this will be declared like the dimensions from 3 down to 0, or we may use the range 1 to 4 also. Okay, next what we need to do is, so we declare this full component within this architecture of adder 4. Okay, so 4-bit adder. So that's why here 4 full adders will be there. So here you can see that, here you can see the structural description of a 4-bit adder. So what is the syntax? I told that entity space entity name. So you are using 4-bit adder. Let's give the name as adder 4. Then is keyword. Then you have to write this, declare this port. So here A, B, we are declaring 4-bit vectors where A and B, these are the inputs as I discussed here. This is A, and let's say this is B. So A, B, all these are 4-bit vectors, and these are all inputs. So how you can declare this? So A comma B colon, mode is in, and the type is what here? Bit underscore vector. So the type we can mention bit underscore vector, and this is 3 down to 0. Means A3, A2, A1, A0, B3, B2, B1, B0. Okay, and what are the other inputs? That is, CI or carry in. So there are 3 inputs, that is A, B, and carry in, that is CI. Okay, so here, but these A and B, these are what? Input bit vectors, but this is what? Bit. So that's why we have declared them separately. Okay, so that's why here we declare it, then a semicolon, then CI. This is also mode is in, but the type is bit. Here the type is bit vector, and the CI, this is type is bit. Similarly, next, as you know, the output is what? S. Sum is S. Okay, so sum, we have taken the variable name as S here, okay, for sum. So here, this is what? Mode is out, and type is bit vector, 3 down to 0, and CO, this is the carry out. Okay, so CO, this is mode is out and type is bit. Next, you have to write this end keyword and then write this entity name, that is adder 4. Okay, so this is the entity declaration. Okay, so this is how we need to do the entity declaration, and then you have to do the component specification, that is similar to your entity declaration in the full adder. Next is the component specification. Okay, so component specification which will do inside this architecture declaration. So what is the syntax you see for architecture? You know, architecture name we have given as structure, then of keyword, then entity name is adder 4, then each keyword, then you have to do the component specification. So how you can do that? This is similar to your entity. So you can just see that here instead of entity we are using the keyword component, then the name of the component is full adder. We are using 4 full adders, so each of which is one component, so full adder. Then this is not there, so that is the only difference that you can see how we can declare this entity and how we can declare this component. So here each keyword is there, here each keyword is not there. Then you can see the port. So port for each individual full adder, we are taking this what X, Y, C in. These are the inputs. So type is mode is in, type is bit, and C out sum. These are the outputs. So mode is out, type is bit. These are individual, means one bit we are taking. So this is what you can see that this is adder 4. So here input is of type 4 bits. So we are taking bit vector. So here each component is a full adder. So that will add what? 2 bits, individual bit along with Cn. So all these are what? Individual bit. So that's why the type is, you can see, bit. Then similar to your this entity declaration, write the end keyword. Then here you can write this component. Component is a keyword that is written in bold letter. As you know, there you write what component name here, writing entity name. In case of component, you can see that just we have written this keyword component. Then next is what you have to declare these signals, whatever the internal signals. So what is the internal signal over here that you can see? C is the internal signal. Okay, because here you can see that in 4-bit adder, you can see from this is the output and this is input to this. These are all internal signals, C1, C2, C3. All these are internal signals. So you need to declare that within the architecture declaration. So signal C, like in the previous example you have seen. So signal C here, but this is what? A bit vector. Okay. So signal C, here you can see that mode is not there. This is an internal signal. Okay. And then the type, bit vector. So 3 down to 1. We are using what? C3, C2, C1. That you can see C3, C2 and C1. So 3 down to 1. Okay. Then next you have to instantiate 4 copies of the full adder. As you can see that there are 4 copies of the full adder. So here you have to mention the level. Okay. So this you have to specify what within this begin and end. Okay. This is the level colon. You have to specify the name here, name of the component. Okay, name of the individual component, and name of the component is full adder. then you have to use this keyword port map. Then within this, you can see that for the FA0, here you can see this is the FA0, this is FA1, this is FA2, this is FA3. Okay. So here, what are the inputs and outputs that you can see? You need to specify A0, B0, CI, these are the inputs, and C1, this is the output carry out, C1, and sum, this is S0. Okay. So all these you have to specify as a list. Next, like FA1, so for this inputs are A1, B1, C1, and the output is that you can see carry out is C2, and sum is S1. Like this, you have to specify all these four. Then end keyword. After that, you can write this part. This is the architecture name is structure. Okay. Okay, so while doing this simulation, we can place the entity and the architecture for the full adder and this adder 4 together. You can place in one file and you can compile. Or we could compile the full adder separately. You can compile and we can place it in the library which is linked in when we will compile the adder 4. Okay. So you just understand this example. I have not actually installed this software for the BSDL. The next class I'll see that. I'll show you the demonstration. So like we can use the model sim BSDL simulator for this. So how to do the compilation? Here you can see we will take one example like we have to we are going to add this part 1111. See here. Okay, so this, sorry. Okay, 1111, another is 0001. Okay, so first what you need to do is you have to put the signals on the output list. Like you'll write what add list. So what are we are using A, this is the input and B is the input, and CO, this is the carry out, and then CI, this is the carry in, and S is the sum, and C is another bit vector. A, B, S, and C. You know, all these four are bit vecters. So, like A is the bit vector that is containing the value 1111. B is the bit vector that is containing the value 0001. Okay, and C here, as you saw that this is the internal signal that is the bit vector. So C3, C2, C1. And S is the sum that will find. So first A we are setting what set the A inputs to 1111 and B is what 0001. And next we want to set the carry in to 1. So what will write? So while setting or initializing these values, what we are writing? Force. Okay. So force. Then here we are writing this input signal A and what is the value you want to assign. And force B, 0001. Then force CI. So what is the value of carry in our CI? We are setting it to 1. Then run, you have to specify the time. Let's say 50 nanoseconds. Here we are, as we have assumed that for the propagation delay of 10 nanoseconds for each of the components. So like here you have specified if you are taking 50 nanoseconds, so it will be sufficient to get the correct result. So like 4 adders are there. After actually 40 nanoseconds will get the exact output. Okay, so that's why to be on safer side you can run it for 50 nanoseconds. If you are running for 30 nanoseconds or 20 nanoseconds, so you will not get the correct output. Okay. So we'll run the simulation for 50 nanoseconds. So this is more than enough time for the carry to propagate throughout all the full ladders. So here like you see this example, what we have taken that value of A equal to what? 1, 1, 1, 1. So this is the value of A, you can see. This is A3, 1, A2, 1, A1, 1, A0 is 1. And similarly, next value of B is what? 0, 0, 0, 1. So B3 is 0, B2 is 0, B1 is 0, B0 is 1. Okay. So these are the value of AB. Next we can see that first we have taken the value of CI equal to 1. So this is the carry in our CI that we have taken as 1. And as you know, rest everything. So that will be by default initial S to 0 sum. This value is 0, S3, S2, S1, S0. Okay. And C out is 0. And your C3, C2, C1. All these are zeros. Okay. Now the sum and carry, this will be computed by each of the first adder. And that will appear at the first adder outputs 10 nanoseconds later. Because here we are taking the propagation delay of 10 nanoseconds. So as you can see here, first what you can see value of A is 1, B is 1, and this C in is 1. Okay. So let's see here. You can see this example here. First value of A is 1, B is 1. The LSB you can see. Okay, A is 1, B is 1, and C in our CI value is 1. Okay, so now what will be the value of sum and C out? So as for the full adder, as you know, you see 1, 1, 1. What is the output? Again, see sum S equal to 1 and C out is also 1. Okay, so here you can see that. So after 10 nanoseconds, this is the time equal to delta. Initially you can see. Initially, these are the values. Now, after 10 nanoseconds. So after 10 nanoseconds, it is computed. Now value of sum equal to 1 and C out equal to 1. Okay. So again, when this will propagate, this will take another 10 nanoseconds. Okay. So here you can see at time equal to 10 nanoseconds, this is the situation. Okay. Here we got what? That the value of C out equal to 1. But this will take another 10 nanoseconds to propagate. Okay. This will take another 10 nanoseconds to propagate. So that's why here now, before that, what is the value you can see? This is what? 0. Okay. So means here you see A value is 1, B value is 0. This one will take 10 nanoseconds. So that's why here the value is 0. So 1, 0, 0 means here A value is 1, B value is 0, C in is 0. So now you see what will be the output. Sum equal to 1 and C out equal to 0. So that's why here in this figure you can see sum equal to 1 and C out equal to 0. Similarly for this you can see again here 1, 0, 0, okay, like the previous 1, 0, 0. So here again 1, 0, 0 as you got here, sum equal to 1, C out equal to 0. Sum equal to 1, C out equal to 0. So here also 1, 0, 0, sum equal to 1, C out equal to 0. This is the situation after 10 nanoseconds. Again, after 20 nanoseconds, what will happen? Now this have been propagated that now the value of this is what? 1, this Cn. This is 1. Value of A is 1, B is 0, Cn is 1. So 101, you see, 101. So sum equal to 0, C out equal to 1. So here we'll get sum equal to 0, C out equal to 1. Okay, so this is changed. Now sum equal to 0, C out equal to 1. So similarly after 30 nanoseconds, after 40 nanoseconds. So after 40 nanoseconds we'll get the correct result. So that is what just see here what will be the value. So we are computing this. So what is the value? Normally you can calculate and we'll get that exact value after 40 nanoseconds only. So this is as you know, this is A, this is B. We'll find out sum S. Here first A value is 1, B value is 1, Cn we have set it as 1. As you can see, we have set the value of Ci, that is 1. Okay. So let's check this. Cn is 1, Ci equal to 1. Okay. So A1, B1, Cn 1. So what will be the value of sum? A1, B1, C1. The value of sum is what? 1. The value of sum is 1. And C out is 1. So which will become now Cn. Okay. So now you see A, B, Cn 101. So 101 you see. That is sum is 0, C out is 1. So sum is 0. C out is 1. Now you see A, B, Cn. So 101. So 101 again. Okay. So 101, that is sum is 0, C out is 1. Sum is 0, C out is 1. Which is the Cn now for the next. So now again 101. So 101. So this is 0. Okay. And C out equal to 1. Okay, so this is what we'll find out. 1111 plus 0001, Cn value is 1. So what do we obtain? The result is 0001. So 0001 with a carry of 1. Okay, C out or carry of 1 at time equal to 40 nanoseconds. Okay, time equal to 40 nanoseconds. You can see the sum 0001. So this is what you can see, like you are taking the time nanoseconds. First 0, then you can see initially all are zeros. Then delta value, this is plus 1 at the time. We are taking the value of A equal to 1111, B equal to 0001. As you know, there this C out is 0. This C is 0, C3, C2, C1, all these are zeros. Ci is set to 1. And sum, we got what at first, you can see this is the at time equal to, this is what 0 delta. Here we are getting sum 0, 0, 0, 0. So this is 0, 0, 0, 0. Okay. And here you can see that the value of C. C is here what? C3, C2, C1, that is nothing but 0, 0, 0. So here 0, 0, 0. Okay. CO, this is the output, that is you can see 0, 0 here. Okay. Like after 10 nanoseconds, you can see here. What is the value of A? You can see this is the value of A. AB that is not going to change. A value is 1111 fixed. B value is here. A value is 1111, B value is 0001. And here you can see what is the sum 1111. 1111. Okay. And what is Ci? That is 1. Then what is C? You can see 001. Okay. here. And what is CO? That is 0. So this is how we'll find, and after 40 nanoseconds we'll get the correct result, that is what sum is 0001, okay, with a carry, that is average 1. Similarly, after that it has taken another another example after 50 nanoseconds. So it has set the value of CI to 0, and value of A it has taken 0101, B it has taken 1110, and then it is run for 50 nanoseconds. So similar to this, we'll get another here finally for this. Okay, you can see here 0101. Then another is 1110. Okay. So here CI is set to 0. So this is your A, this is B, and this is initially Cin is this, Ci equal to 0. So that is 100. You can see that 100. Sum is 1, C out is 0. So sum is 1. C out is 0, which will become C in for the next. Again, A, B, C in. So 0, 1, 0. So 0, 1, 0, you see that S is 1, C out is 0. So 1, C out is 0. Next, 1, 1, 0. So here you can see this is 0, C out is 1. So 0, C out is 1, which is C in for the next. So 0, 1, 1. 0, 1, 1, which is 0. And having a carry, C out equal to 1. So 0, 0, 1, 1 and C out is 1. That you can see 0, 0, 1, 1 with a carry of 1. This is our time equal to 80 nanoseconds. Okay. So it's for 40 nanoseconds. We have run it for 50 nanoseconds. Okay. Then it will also take 40 nanoseconds. We'll get this output after a time equal to 80 nanoseconds. So this is 0011 with a carry of 1. So 0011 with a carry of 1. Okay, so as we discussed here, we constructed the BSDL model using the entity architecture pair. So we use the 4-bit adder model that demonstrated the use of BSDL component to write the structural BSDL code. So you can see the component declaration form. We have used component space component name, right here. Okay. Component space component name, then port, list of interface signals and their types we mentioned. Then you can see this is the syntax, and this is the keyword, then component, this is the keyword. So end component. So this is what we have written, how we have declared this component. So the port clause that we are using in the component declaration has the same form as the port clause which we have used in the entity declaration. Okay. And you can see the level. Okay. So the connections to each component used in a circuit, these are specified using the component instantiation statement. Like there are 4 full adders. So you have specified the level like FA0, FA1, FA2, FA3. So that these are the levels, column. Then you have to specify what the component name. Component name is full adder. Then the keyword port map. So you can see that the full adder. Then port map. Then a list of actual signals. So what are the actual signals that we have put? Like here A0, B0, CI for the first full adder. A0, B0, Ci, these are the input signals. And C1, S0, these are the output signals. All these signals, actual signals, you need to specify. Okay. Okay, up to this, is there any doubt? Okay. Okay, next we'll see the use of buffer mode. Like we have seen the mode in, out. Okay, we'll also see the use of buffer mode. Now let us consider this example. So we are assuming all the variables. Here we are using A, B, C, D, E. So all the variables are having the value 0 at 0 nanoseconds. But here let's say A is changed to 1 at 10 nanoseconds. So here the example you can see that this is the entity declaration. Entity name is gets, then E is keyword. Then you have to declare the port. What are the input signals? That is A, B, C. Okay. So these are the input signals, and D, these are the output signals. Okay. And this is architecture. So you have to declare this architecture. Architecture name is your specified example. Then off keyword. Then you have to specify the entity name. That is, entity name is gets. So then each keyword. Then you have to write this architecture body within the begin and end. So you have specified what D equal to A or B. Okay. So this is architecture. Okay. And E equal to C or D. Okay. So here, this is the gate that you can see. Now, what you're saying that this code is not actually compiled. Here you can see that this statement 2, this uses what? D on the right side of the assignment statement. Here you can see D we have used on the right side of the assignment statement. Okay, so that's why this should be either in out or buffer mode. Okay, because here D you can see that this is present on the left hand side. Okay, and here D is present on the right hand side. Okay, so D you can see that we can say that this is output for this what? This gate, that is A or B, and this is the input to this gate, that is what? C or D. So that's why this D should be declared either in out or buffer mode. But here what we have specified that this is the output signal. Okay, so that's why here there will be an error and this will not be compiled. Okay. So either we have to use the in-out mode. In-out mode means that becomes truly bidirectional signal. Okay. but this is not an external input. This is not an external input to the circuit. Okay, so that's why here buffer will be more appropriate. Okay. As this is not external input, this is the internal signal. So here buffer mode will be more appropriate. This is the out for this and in for this. So buffer mode will be more appropriate for this. So here the changes you can make is that you can see that earlier we have specified ABC as in bit, DE as out bits. So D we have to specify it as buffer bit. So you give semicolon, then D is the buffer bit and E is the out bit. Then AND keyword, then you have to write the entity name. Rest all are same. Okay, so whatever you see here. So only this D you have to specify as buffer bit. Okay. So now, like if the value we are saying that the change in A, let's say it is changed at 10 nanoseconds. If then the value for D, if A is changed to 1, now the value of D will also become 1. Okay, so that is after 15 nanoseconds. That is 10 plus 5. After 15 nanoseconds. After 15 nanoseconds, it will become 1 because A is 1, so 1 or something, so that will become 1. And here also there is a delay of 5 nanoseconds. So here D becomes 1, so that's why C or D. So this will also become 1, that is E will become 1 after what? 20 nanoseconds. So that is again another 5 nanosecond delay. So this E will become 1 after 20 nanoseconds. Is there any doubt here? Okay, I'll just take attendance. Okay, all of you tell your registration numbers. Asna.
Yes, sir.
Okay, just tell your registration number.
2041 005 002.
Okay. Next, Avilasa Panda.
Yes, sir.
Yes, your registration number.
Sir, 204
Yes.
101
Yes.
6027.
Okay. Next, Swatik Das. Swatik Das.
Yes, sir. Yes, sir.
Okay. Your registration number.
204 100 4035.
Okay. Next, Siddhant Sarup Malik. Okay, next. Siddhant Sarup Malik. Okay, next, actually, who are listening, tell me your registration numbers who are left. one by one.
Yes, sir. It's 20410 16177. Hello.
Yes, okay.
Okay.
Sir, 204-100-2035.
204-100-2035.
Yes, sir. Arpan.
Next, Supriti.
204-101-9297.
Next, Sweta. Okay.
Shwetapada. 204-100-2040.
Next, okay, for whom I have taken the attendance, you may leave. Who is remaining? Yes.
Yes, sir.
Yes, your registration number.
It's 204-101-8112.
Okay. Next, who is left? Now, only 8, rest 2 who are left.
Sir, Angana's registration number is in the chat box. Her mic is not working.
Okay. You just tell that message is not showing. You just tell a registration number. Do you know? Okay, I have mentioned the name. Next. Yes.
Sir, I'm telling the registration number. It's 204-101-3058.
Okay. Anyone else left or it's over? Okay. Okay, thank you all of you.